welcome back. So today I'm going to take up this important theorem called very important theorem which brings in a lot of applications for singular value decomposition. So it's like it goes like this. Uh, Let A be a M cross N real matrix of rank R. Okay, and now we are looking at some k which is strictly less than R. That means we are looking at, in some sense, we are looking at low rank approximation. And if you recall our earlier discussion, basically we are trying to connect rank deficiency and SVD. So that's why when we say k is less than R, strictly less than R, we are looking at a low rank approximation of lower rank approximation of A, and let us define a AK matrix like this. AK is equal to it is basically sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose and so on up to sigma k UK VK VK transpose. So basically what you have done is these additional terms sigma k plus 1 UK plus 1 VK plus 1 transpose and so on up to sigma R UR VR sigma R VUR VR transpose. These terms we have dropped them. So these further terms have been dropped them, and this matrix has this is basically a singular value decomposition of basically the matrix AK. It directly provides you the thin singular value decomposition of the AK matrix, and since it has k non-zero singular values, so therefore its rank is obviously k. And why is sigma k greater than 0? Because if the matrix has original matrix has rank R, then I know that sigma 1, sigma 2, sigma 3 up to sigma R are strictly greater than 0, and sigma R plus 1 onwards, whatever is that remaining thing is going to be equal to 0. So therefore, since I have used the same sigma 1, sigma 2 to sigma k, and this is sigma k is strictly sigma k will be greater than 0 because you are still not reached sigma R, and you know that sigma k is greater than or equal to this and so on, greater than or equal to sigma R, which is strictly greater than 0 because the matrix has rank R. We have already, if you recall in our earlier discussions, we have talked about that we count as number of non-zero singular values, and that exactly is the rank of the matrix. So without any worries, we are able to say that AK matrix is a rank K matrix, and in fact its singular value decomposition is already available, constructed from the, or rather constructed or extracted from the singular value decomposition of this A matrix. Now the main part of the theorem is the following. We are looking at all set of B matrices which are in nearest to the given A matrix, which are nearest to the given A matrix, under one condition, under one constraint. It is a structural constraint that rank of B should be equal to K. So that means you are looking at you are looking at all you are looking at all rank K M cross N real matrices because you are able to subtract them from B, right? A. That means they are actually M cross N matrices. So you are looking at all M cross N matrices of rank R, and you want to pick that matrix B whose distance to A is closest, is nearest, and the distance is measured in the second norm. So therefore our problem is minimize A minus B, norm of A minus B, second norm of A minus B, such that rank B is equal to K. So this B matrix is going to give you the best rank K approximation to A matrix. That's the idea. Because why is it giving you the best rank K approximation? Because it is closest. It is closest to A in some distance measure. The distance measure that has been picked up is the norm 2. So because it is closest to A in some distance measure, and it is that matrix among all the rank K matrices, so therefore this matrix, this solution B can be treated as a rank K, whatever this B star will come out to be, can be treated as the rank K approximation, nearest rank K approximation for matrix of A, for the matrix A. So this is what we want to solve this problem. And what this theorem says is, this problem can be solved using singular value decomposition, and the answer is going to be the matrix AK, which we have already written here upstairs. This answer is going to be matrix AK, and the distance between A and AK is exactly equal to sigma K plus 1. The next non-zero singular value. So this is how close it is going to be. So suppose say sigma K is 0.1. Let us say sigma K plus 1 is 0.01. Then it means that all these rank K matrices will at least have a distance of 0.01 from, at least have a distance of 0.01, the minimum distance. So the minimum distance is going to be at least 0.01 from the A matrix. So if somebody asks you, no, I want something which is 0.001 distance away, that is not possible because sigma K plus 1 is 0.01. So this is the important aspect of this particular theorem. So we'll come to the application of it subsequent to this discussion. First, let us prove this theorem. Okay. So I have already said that AK can be written as U1, U2 to UK, sigma 1, sigma 2 to sigma K, and appropriate zero blocks, and V1 transpose, V2 transpose to VK transpose, which is nothing but U1 sigma 1 V1 transpose, the thin SVD of AK. This I have already said. So therefore from my previous discussion we are already in a position to say that rank of AK is K, because sigma 1 is greater than equal to sigma 2 greater than and so on equal to sigma K, which is strictly greater than 0. So we have established that AK is one candidate matrix for among all the B matrices of M cross N dimension which have rank K. Okay. So now our theorem has two parts, really speaking. Part 1, we want to prove that that A minus B, this distance, is greater than or equal to sigma K plus 1, for all rank k B matrices of the dimension m cross n. So this is one point we want to prove, because we are saying minimum is will be a distance of sigma k plus 1. That means either it will be sigma k plus 1 or greater than or equal to greater than sigma k plus 1. So that's one part we want to show. Then we already have one candidate AK matrix defined here. We already have one AK candidate matrix defined here of rank k. So we just want to check and show that A minus AK, this is the part 2. We want to just show that A minus AK length is equal to sigma k plus 1. So once we have shown this particular part, then basically what it means is, here we showed that all the A minus B lengths for rank k m cross n B matrices is always greater than or equal to, this distance is greater than or equal to sigma k plus 1. And here is a rank k matrix whose distance is exactly sigma k plus 1. Then it means AK is the optimal, because in this greater than or equal to bound, to get the minimum, what really you are interested in is there any B which can give you exactly equal to sigma k plus 1. That means this is a tight bound and equality is achieved. If I am able to find such a AK, then that AK is actually the minimizer to this beautiful optimization problem, which you cannot, like, really speaking, handle it to discussion that you do in first course in optimization kind of a thing. This actually requires a SVD treatment to do that. Otherwise, at least I am not aware of any good proof about it. So to prove this, first of all, let us show the part 1. Let's go in the sequence in which we have defined it. Part 1, for all rank k m cross n matrices B, of course real matrices, we want to show that A minus B is greater than or equal to sigma k plus 1. Okay. So now what I am going to do is, I am going to consider two subspaces. First of all, okay, because first of all, let's take some B. What is the B? B is a M cross N matrix, real, rank K. Again, I am not writing this, but this is all, whenever I say B, I mean this. Now take some B. If you want, you can call it feasible B. In the traditional talk of optimization, this is what would be called as a feasible candidate or a feasible solution, or something like that. Then, if for this B, what is the dimension of the null space? Because this is a M cross N matrix and its rank is K, so therefore the dimension of the null space is going to be N minus K. So let us say that the basis of the null space is x1, x2 up to xn minus k. So let this be the basis of the null space. Basis means what? All these vectors are linearly independent. Second, their linear combination spans the null space of B, and any vector in the null space of the B will have the property that Bz is 0. So if Z is in the null space of if Z is in the null space of B, then we will have a condition that BZ will be equal to 0, and because this is the basis, so if I write this whole matrix as, or so I can write Z as linear combination of some alpha I xi I equal to 1 to n minus k. So every vector in the null space because can be written as a linear combination of the basis vectors. So because this is the basis of the null space, this can be written, and because Z is in the null space, Bz will be equal to Bz will be equal to 0. Now consider another space, and these are vectors from where? These are each xi is a vector from Rn. Why? Because B is m cross n matrix, so the Z has to be a n cross 1 vector, and since Z is the linear combination of the basis vector, so therefore each of the xi vector is a n dimensional vector. Now let me consider another space which is formed by V1, V2, which is formed by the span of V1, V2 and so on up to Vk plus 1. Okay. Now what is the dimension of this span? Whatever this space is, what is its dimension? Its dimension is k plus 1. Why? Because V1, V2 to Vk plus 1 are orthogonal vectors, and orthogonal vectors are always linearly independent. Orthogonal vectors are always linearly independent. So because these are orthogonal vectors, they are linearly independent. So therefore if I look at the span of this, it will create a vector space of dimension Vk plus 1. Now a vector here in this span, let me just for the sake of calling it some name, let me give it a name E. So a vector in this span can be written as some beta I Vi sigma I equal to 1 k plus 1, which is like beta 1 V1 summation plus beta 2, beta 1 beta 2 are scalars up to beta k plus 1 Vk plus 1, which if you write this as the matrix, what should I call this matrix as? Let me call this matrix as some V bar matrix times the beta vector, where V bar matrix is V1, V2 to Vk plus 1. This is n cross k plus 1 matrix, and beta is a k plus 1 vector, and let us call this vector on the left hand side as y. So if you look at y transpose y, that is beta transpose v beta, which is equal to beta transpose b, which means to say that length of y is nothing but equal to length of the beta vector, which is obvious, right? Because this is an orthogonal matrix. When you if the beta vector is pre-multiplied by it, it will not change the length of it. We know of this. One more thing that I want to say is these beta i's can be thought of as coordinates. Along direction V1, direction Vi. I mean, we have seen this kind of a 2D example earlier also. Let's say this is a two-dimensional space, and I have a vector here then these are the original directions E1, E2, and its some coordinates are x1, y1. Now consider that your V1 orthogonal vectors V1 and V2, they are orthogonal, so they should be perpendicular to each other. They come out to be this. Again, this is the unit length vector here. Let's say 1, 2, 3, 1, 2, 3. This is the unit length vector here. So appropriate unit length vectors would be somewhere here, somewhere here. So these are the unit length vectors along the direction V1 and V2. So if you project this is going to be beta 1, this is going to be beta 2, and beta 1 square plus beta 2 square is going to be same as the length of the square of the vectors of this, which is same as x1 square plus y1 square. So what I am just trying to sort of say is, this is giving you another coordinate system. The proper orthogonal vectors give you a coordinate system, and the scalar multiplier which gets associated with them is nothing but the coordinate on or along the projection of it. And how do you calculate it? You calculate it by just take this expression, here and multiply this by, say, Vi say V2 transpose. So let's look at this. What is V2 transpose Y? So you are going to multiply this by V2 transpose. Now what is V2 transpose V1? 0. What is V2 transpose V2? 1. What is V2 transpose V3? 0. What is V2 transpose Vk plus 1? 0. So therefore, all these terms will go away, and what is going to survive is only beta 2. So therefore, this will nothing but get you equal to the beta 2. So projecting, this is projection, right? We have seen Cauchy-Schwarz inequality. Projecting Y on Vi, which is operation Vi transpose Vi, gives coordinate along the axis Vi. This is what I am saying. Just remember, what I am trying to sort of say is that orthogonality gives you a very good geometry, and it also gives you a very good algebra. So carry both with you, carry the geometry also with you, carry the algebra also with you. Now let us come back to what is the point that I was trying to say. I have created, let me recap, I have discussed now two subspaces. One is the null space, which I called it as, did I call it as E? What did I? No, this I didn't give it any name. So let me call this as N, which is the subspace formed from this N minus K. The basis of null space of B matrix. So this subspace NB, is nothing but the span of is the null space of the B matrix, and its basis is given by this. Basis of the null space is given by this. I took another subspace which is span of V1, V2 to Vk plus 1. Why did I choose V1, V2 to Vk plus 1? Because somewhere it's intuitively, somewhere it is coming here in my definition. I will have to look at this k plus 1 dimensional subspace. This is a very weak way of saying it, but there has to be some way to figure out some connection, however indirect one may want to draw, and that is this connection that I have drawn. I am looking at this particular space. Now I claim that NB intersection E, which is to say that span of x1, x2 to xn minus k intersection span of v1, v2 to vk plus 1 is non-empty, not equal to phi. It is not non-empty, is not a zero vector. In other words, it will have some non-zero vector coming in it. How? I can just do a dimensionality check. Suppose there is no common vector in this span. Right? Suppose in this intersection, suppose there is no common vector in this intersection. Then it would imply that x1, x2 to xn minus k, comma v1, v2 to vk plus 1, this would be set of linearly independent vectors. If you have a doubt, come back to me, but I think you can easily check this out. That if they don't have anything in common, then they will be linearly independent vectors. Now, if that happens so, then dimension of Rn will at least be n minus k plus k minus 1, which is equal to n plus 1. But is this possible? It is not possible. The moment I say that the dimension of Rn, it is an n-dimensional space, it cannot have a dimension of n place. So where did I go wrong? Contradiction. Where did I go wrong? I went wrong in assuming that there is nothing in their span. This is what there is no vector in this span. This is where I went wrong in my assumption. So what is the conclusion that I have come to? I have come to the conclusion that span of this is in these two subspaces will have some non-zero vector in their intersection. So let Z be one such vector. So Z is one such vector. So therefore, first of all, the Bz is going to be equal to 0. And Z can be written as this matrix V under bar times some vector beta. In other words, it can be written as beta I Vi I equal to summation 1 to k plus 1. Okay. Now, what we want to do, we have taken B to be some m cross n matrix of rank K, and what is it that we are trying to show? Part 1, what is it that we are trying to show? We are trying to show in the part 1 that norm of A minus B is greater than or equal to sigma K plus 1. So therefore now let us take the norm of A minus B, square of the norm of A minus B. And this is going to be greater than or equal to A minus B times Z square. Okay, so I should make one more thing. I said let Z be one such vector, but I should say something more. Let Z be one such unit length vector. So there is some vector Z which is in the intersection, we know that non-zero. Just scale its length to 1, but let it be a unit length vector. The moment I write it as unit length vector, then I know that maximization over all such unit length vectors will give me the square of the norm of A minus B. So therefore, if Z is just one some unit length vector, then whatever I get here, the maximum is going to be either this or greater than this. If it is the maximum, then you have got the square of the second norm of A minus B. Otherwise, the square of the norm of second norm of A minus B is greater than this. So the choice of unit length vector is important. Now this, however, can be simplified as AZ minus BZ square. But what is BZ? BZ is 0. So therefore, this is going to be equal to square of the length of this is going to be equal to square of the length of AZ square of the length of AZ vector, which for A, if I write it as if I write for A as U sigma, okay, so U sigma V transpose, and for Z I am going to write it as V bar beta and then square. So this is going to be equal to, because U is an orthogonal matrix, right? But what is V transpose V bar? V transpose is V1 transpose to Vn transpose, and V bar is V1 V2 to Vk plus 1. So therefore V1 transpose V1 is 1, 0, 0, 0. V2 transpose V1 is 0, Vn transpose V1 is 0. Then 0, V1 transpose V2 is 0, V2 transpose V1 is 1, 0, and 0, 0, 0, 0, so on up to last entry, the K plus 1th entry, the last, I'm sorry, Vk plus 1. So this is n cross n matrix, this is n cross K plus 1 matrix, this is n cross K plus 1 matrix, and so this is going to be equal to K plus 1, you will get a 0, and then something and so on up to 0. So you will get this as n cross K plus 1 matrix, in which so if you want will have some zeros coming here, some zeros coming here, and then some more zeros coming here. So this is the k plus 1 times k plus 1 identity subblock of this matrix, and the remaining ones below that is going to be equal to 0. So now when you multiply this and the diagonal matrix, so what will happen? You will pick the first k plus 1 singular values, and so you will get essentially this as square of the length of sigma 1 beta 1 sigma 2 beta 2 and sigma k plus 1 beta k plus 1. You will get the square of length of this, which is nothing but sigma 1 square. Instead of beta 1 square, I am going to write it as V1 transpose Z square and sigma 2 square V1 transpose Z square. Actually, I could have written beta also, there was no problem. But anyway, I know that I have done it, I have done it. Sigma k plus 1 square Vk plus 1 transpose Z square. And this, because sigma 1 square is greater than or equal to sigma k plus 1 square, so therefore the first term, see this is, I should write it. See, this first term is greater than or equal to sigma k plus 1 square. This second term is also greater than or equal to sigma k plus 1 square. And this last term is obviously greater than or equal to sigma k plus 1 square because it is sigma k plus 1 square. And these are all non-negative terms being square. So I can now convert this equality into a greater than or equal to type of inequality by taking this thing out common and writing this as beta 1 square plus beta 2 square up to beta k plus 1 square. But what was my z vector? It was a unit length vector, and these are its coordinates in the coordinate axis v1, v2 to vk plus 1, and all the coordinates are there only because of the fact that it was a linear combination of v1, v2 up to vk plus 1. So therefore we know that this square sums to 1. So therefore this becomes equal to greater than or equal to sigma k plus 1 square. So what have we proved? We have now proved that if we look at rank of B equal to K and nearest, we are looking at nearest rank K matrix to the matrix A, which has a rank R, then this distance will have to be greater than or equal to sigma k plus 1 square. So therefore means you can only come as close as the value sigma k plus 1. You can come only as close as sigma k plus 1, but not any nearer than that. You will never get a B matrix which is any nearer to A and still has a rank K nearer than this value sigma k plus 1. Now the only thing is, this is an inequality. Does any B star meet it at sigma k plus 1 distance? That is the question. Answer is yes. That's the second part of our theorem. It is this particular matrix. This is rank this is rank K. We already discussed that this is the rank K. This is a rank K matrix. In fact, this is the singular decomposition of the AK itself, which has K non-zero singular values. So now, only thing that we need to really check is what is this value. So you are looking at K minus AK, which is, what is A? A is I equal to 1 to R. A is I equal to 1 to R. Sigma I UI VI transpose minus, what is AK you are looking, I equal to 1 to K sigma I UI VI transpose. So the first K terms from here will cancel with this summation. So you will be left with sigma I equal to K plus 1 to R sigma I UI VI transpose, which is to say sigma K plus 1. This is a matrix UK VK plus 1 transpose and so on up to sigma R UR VR transpose. So now what is the rank, this is already the thin SVD singular value decomposition available of this particular matrix. What is its largest singular value? Sigma K plus 1. So therefore I know now that A minus AK is equal to sigma K plus 1. So now put 2 and 2 together. Part 1 said in part 1 we proved that this particular result, and in part 2 we have shown that AK matrix actually gives you, it's a rank K matrix which exactly give you which is exactly at a distance of sigma K plus 1. So therefore you are now in a position to, you have now basically proved the theorem. So this theorem basically says that the smallest singular value of A is the second norm distance of A to the set of all rank deficient matrices. It also therefore follows, I'm quoting Golub and Van Loon, that the set of all full rank matrices is both open and dense. I just leave it to you to think about this. And finally, let me close this by giving you the epsilon rank K, epsilon R, if R of epsilon is defined as rank of A comma epsilon, and you may recall this definition that this was defined as minimization of all, you are looking at rank of, so you are choosing a matrix B of minimum rank such that it is within the epsilon distance of A. So this was said to be the epsilon rank of the, this we had defined as the epsilon rank of the matrix, that is look at all matrices within epsilon distance of A and choose the one which is of minimum rank. So then sigma 1 is greater than or equal to sigma 2 and so on, basically is, this is where this counting I have to do to decide this number. This is not given to you. What you want to make sure is this singular value is strictly greater than epsilon, and then subsequent ones are sigma, are either sigma, those singular values are either sigma or smaller. P is the minimum of m and n. These are the total number of singular values. They could be 0 also. So what we are saying is, suppose I have defined epsilon as 10 to the power minus 4, and the singular values are like 10, 5, 1, 0.01, 0.001, 10 to the power minus 6, 10 to the power minus 8, and say 2 zeros. Suppose these are the singular values. So then what will happen is, so this first singular value is greater than 0, second singular value is greater than this threshold, third is greater, fourth is greater, fifth is greater. The sixth singular value is strictly smaller than epsilon. The sixth singular value is strictly smaller than epsilon. So therefore the epsilon rank of this matrix, which is also called sometimes as the numerical rank of this matrix, will be 5. So this is how we use this this very important theorem to approximate a m cross n matrices by a smaller by a lower rank approximation. I think I'll stop here for now. Thank you.